Okay, great stuff. We're going to be reviewing the 2023 computer science paper on paper 1. 2023 was the paper where paper 2 was the one that everyone found really difficult, but this is paper 1. And for the most part, people thought it was a fairly fair paper. So let's go to question 1. At the beginning, this is pretty classic. We're going to start with data representation questions, binary, denary, etc. First question is having us do a bit of a review. Tick one box to identify the statement about binary that is true. Binary digits can only be in the value 0, 1, or 2. The leftmost bit of a binary digit has the smallest value. The binary is used because computers are made out of switches that can only be on or off, and the smallest whole number that can be stored in 8 bits is the number 1. And the answer is, absolutely, the answer is this one. I mean, this is definitely wrong because binary only has 2 values. Yeah, it's C. There you go. And of course, it's the rightmost value would have the smallest value. Okay, a bit of conversion. We got these values. Can we convert them from one to another? So in binary, that's the value 7. In hexadecimal, that's the value 7. In denary, we'd write down 7. Well, that's an easy mark right there, isn't it? It's kind. For the next one, we've got denary, binary, hexadecimal. As a reminder, maybe hexadecimal, that's lots of 1s, that's lots of 16s. So it'll be 3 16s, 48 plus 1, which makes 49. For binary, what we'd have to do is write out the grid or the unit, which would be from 1 going up. We write the units as we go along. And what we have to do is we're going to have to make up the number 49 effectively. And if you remember the way we did that is we said how many 128s go into 49? And the answer is 0. How many 64s go into 49? None. How many 32s go into 49? 1. 49 take away 32 is going to leave you with 17. How many 16s can go into 17? 1. And therefore leaves you with 1. Next question, we just need to do the denary bit. So I do the same bit over here. In fact, I'll do it from the hexadecimal viewpoint. What do I write here? How many units do I write here? 16. And the other one would be 1. To calculate the figure, I'd have to do 6 times 16 plus, well, 1 times 6, so 6. 5 16s is 80. So 6 16s must be 96 plus 6, 102. And then finally, we got to do the same inversion. This is a great opportunity because I think this is the one that people do struggle with, which is turning numbers into hexadecimal. Yeah, this is a question that people do often struggle with, which is converting values to hexadecimal. And do you know what I'm going to do? I'm going to do both from a perspective of turning it from binary to into hexadecimal and denary. So we do both ways. So if we're turning it into binary, into hexadecimal, do you remember what we do? We split it into a nibble. What is a nibble? A nibble is 4 bits. We can go like that. And so the first value on the left would be the value 15. And on the right would be 4. Remember, in hexadecimal, you wouldn't write 15 because when you get to 10, it becomes A, 11 would be B, 12 would be C, 13 would be D, 14 would be E, so ultimately it would be F and 4. But I said I'd do it both ways. So this value 244, to turn that into hexadecimal, so what you need to do if you're trying to convert directly from denary into binary is you need to see how many 16s can fit into the number. The number we have right now is quite large, 244. So how many whole 16s can we put into it? The shortcut is to immediately do 10 16s. That makes 160. But I can go further than that. 5 16s is 80. So 15 16s is 240. We're not going to go any further than that. That would be 15 again. And that's 240. You had 244 originally. So 244 take away 4 is 4. However, on the left-hand side, we wouldn't write down 15 again. What would we write down? 4. And as somebody in the audience was just mentioning, I guess if you do it both ways, you can check your answer. I guess the other point being is that you don't know what kind of question is coming up. It could be a question asking you to just do that, and you're not given the binary. Hard to say. All right, let's continue. Okay, tick on the box to do the largest file size. As a quick reminder, a bit is a single 1 and 0. A nibble is 4 1s and 0s. A byte is 8 1s and 0s. And from there, you just count in bytes. the one that just drives me crazy, that people keep forgetting it, a kilobyte is a 1,000, thank you, right? Hence a kilogram, a kilometer, right? 1,000. The next one up, a million bytes or 1,000 kilobytes would be a megabyte. So we're going to go K, M, what's next? Yeah, G, so that's giga. I could walk in my handwriting, I do apologize. So that's a billion bytes or 1,000 megabytes or a million kilobytes. The next one is terabyte, so that's a trillion, 10 to the 12, and finally petabyte. And you do actually need to learn up to a petabyte, even though petabyte is not realistically a storage value that you're probably going to come into very often. Huh? Yeah, there's like yottabyte, exabyte, etc. There's, yeah, trust me, it's like works in the areas of physics, so therefore there will always be some number. And somebody somewhere, like, it will describe the number of the amount of data that's stored in a YouTube server, and it'll be way bigger than a petabyte. All right, anyway, so 2 million bytes. I mean, the nice way to answer a question like this is to put it into the same. So I reckon 2 million bytes, aka, would be, thank you so much for volunteering, Ibrahim. 2 million bytes, we call that much. Completely agree. 2 megabytes. So that's 2 megabytes. 2,300 kilobytes in megabytes would be 2.3 megabytes. 200 megabytes is in megabytes. And then finally 0.1 gigabytes is 100 megabytes. And then we can quite easily see which one the answer is. What's the answer? The one that's biggest? C. Well,
500,000 bytes.
So that's how many megabytes is 4,500,000 bytes?
That'll be the equivalent to 4.5
4.5
megabytes.
megabytes. Somebody else gets an opportunity to join in. Thank you, Abdul. 450, go. 450 kilobytes this is, though. What do you reckon? No, in megabytes, what would you make it? What would 1,000 kilobytes be? So 450 kilobytes would be 0.45 megabytes. Then we got 4.5 megabytes, so that's a tie. And then finally, 0.45 gigabytes in megabytes would be 450. So therefore, the answer is, and as clearly it says on the question, it's a valuable lesson, isn't it, fair play? I didn't read the question. I do apologize. I answered it by finding which one's the largest, and it quite clearly says, tick the two boxes that are the same. Quite right too. Next question, binary addition. Binary addition, don't panic. Where do we start, on the right or on the left? On the right. Why don't you give it a go? So we start on the right. 1 plus 0 is going to give us 1. I'm going to put the carry underneath it. 0 plus 1, that's 1, 1, 1. Here we go. 1 plus 1 is going to give us 2. Do I write down 2? No, I write down 0, and I carry the 1 underneath on the next side. 1 plus 0 plus 1 is going to give us 2. So I'd write down 0, carry the 1. 1, 0, and 1 is going to give us 2. I do 0, carry the 1. And then finally, what is that called? Overflow, error. Hence, if I don't catch it and do something with it, it's going to give me the wrong result. Identify the binary shift that has been applied to an 8-bit binary number. If I shift to the left, what do I do to the number? Times it by however many I shift it by. I.e., if I shift it by 1, left shift by 1 times it by, shift it by 3, 8, 2 to the power, isn't it? So shift it by 1 to the left is 2, 2 to the left it's 4, 3 to the left it's 8, 4 to the left it's 16, etc. 2 to the power of the shift. If I go to the right, divide by 2, 2 to the left, 2 to the right, divide by 4, 4 to the right, divide by 4 to the right, divide by 16. Identify the binary shift that's been applied to an 8-bit binary to get this. All right. I know what it is. Who else knows what it is? Angie, what do you reckon? 3-bit left shift. Because what's happened is those have gone on by 1, 2, 3, and then you've got 3 on the right. It's been padded with 0, so it's 3 left. Shift. Beautiful. A student, so this is question on networks, is performing a range of actions on the internet using their computer. A range of protocols are used for the transmission. Definition of protocols? A set of rules that govern communication. I don't know if there's a question. I just, and the web servers they're accessing. So they're locally, they're on their network. They're having to go through the internet to access these web servers. Complete the table by identifying the most appropriate protocol for each of the tasks the student is performing. Why don't we, since we have a moment, why don't we just list the protocols we know? So the protocols that we know are HTTP. I'll do brackets S because they're two different versions, I agree. What else? SMTP. Anything else? POP/IMAP. FTP. Yeah, I'll go through them all in a sec. Any others? TCP/IP. Right, let me go through them. Whistle stop tour. I'm not going to write it down. HTTP and HTTPS, Hypertext Transfer Protocol. These are all in the business of transferring web pages. What does the S signify? Security. What provides that security? Encryption. So data is encrypted from one place to another. Hence, if you have a man-in-the-middle attack or it's intercepted, what can you do with the data if it's HTTPS? Nothing very much, unless you have the key, the cipher key to unlock it. SMTP, that stands for Simple Mail Transfer Protocol. This is when you're sending an email to somebody else and it's going up to the mail server. So you as a person sending it up to the server, the mail server, that's SMTP. And from one mail server to another is SMTP. So sending SMTP, I guess you can say that's the S in it, although it doesn't stand for that. Receiving an email is either POP or IMAP, Post Office Protocol, Instant Messaging Access Protocol. You don't actually need to know what they stand for. There is a difference, and I don't know if you really know, I'll say the difference. Both of them are about receiving it. In POP, you take the message from the mail server and it's deleted from the mail server, so it's not there anymore. On IMAP, you take a copy of it and you leave it up there. Nearly everybody uses IMAP these days, so that when you log into your Google Mail, whatever else you're using, doesn't matter what place you're on, you can see all your mail, right? Back in the day, when there was less storage on mail servers, people used POP because maybe you only had 1 megabyte of storage. I swear to God, that's actually what happened, right? I swear to God, right? And often it get filled up. So you had to POP and have it download to your local PC and then freed up space for you to do it. And now invariably people use IMAP. FTP, anybody remember? File Transfer Protocol. Classic place you might be used is maybe uploading files to a web server for your website. TCP, transmission, or downloading, yeah. Transmission Control Protocol, Internet Protocol. This is the protocol that governs transfer of data around the internet. All right, so requesting to view a news web page from a web server. What do we use for watching a web page? HTTP all day, absolutely. If you put HTTPS, would you not get the mark? Yeah, you totally would, right? It doesn't specify it has to be secure or not. If it said, though, securely accessing your bank information, that's where you definitely want to go HTTPS, right? Entering a username and access. Okay, well, there you go. Entering a username and password to access their bank account. HTTPS. If you put HTTP for this one, what could happen? You don't get the mark. God, we are creatures of habit, computer scientists, aren't we? It's not exactly hard to predict. Downloading a text document from a web server. FTP. If you put HTTP, truthfully, you might still get the mark because it's not really specified enough. But I will go FTP. Checking for new emails in their inbox. So you're checking for new. So the downloading part of it would be IMAP or POP. Either way would be acceptable. I'm going to put IMAP, but POP would also be acceptable. Here's a question that comes up, and I don't know if we do very well. This to me reminds me of like, why do we use standardization in networks? Very similar. We struggle to answer that question. I think we feel the same way about layers. Now, I taught you about layers. I remember I did that activity where I got a bit of I think a stick man and I ripped it up. And we taught application layer, transport layer, internet layer, link layer. Now, truthfully, that's not on the spec anymore. You won't be asked about the individual layers. But I taught it to you to understand the idea is that it's done in layers. But maybe we don't know enough about why we do layers. Does anybody idea about why we use layers? Not necessarily. Yes? Go on. Decomposition? Yeah, I suppose it does mean that you can separate your concept into these different layers and focus on them. You know what I'm going to do with you guys? I'm going to do you a solid. I've got the mark scheme right now. All right? The one that... Go on. Yeah, so that's certainly true, isn't it? So if there's a problem on any of the layer, which is links in with what Razan said about decomposition, if there's a problem on each layer, you can debug it and isolate it to that layer. Also, each layer works independently. What I'm going to do is I'm going to read out the mark scheme, and then when you're listening to it, I want you to listen to, okay, what is it that I think I could actually remember and get it myself? There's literally 7 marks here, right? How many marks are there for the 2? So pick out 2 or 3 of the ones that you think you can learn. Okay, so first one is each layer is independent. It's not reliant on each other. So each layer is independent. Second mark is, and it kind of, I mean, really it's saying the same thing as independent. It says one layer can be changed without affecting the others, although ultimately that's saying it's independent, right? This is a bit similar to the advantages of why we use subroutines. Do you remember one of the reasons we use subroutines is you could have different people work on a different subroutine? Do you remember this concept? You could say that different people could work on different layers. So if we think about the transmission control protocol, so when we think about the layers that we learned about, application, transport, internet, link, like link was the physical layer, so you can imagine you've got real engineers putting in cabling, connections up to each other, so you'd have a specialized team for that layer, and you've got a different team maybe working at the application layer because it's about talking about the individual protocols of HTTP or SMTP, some more like software developers. You see, you can have different teams working on different areas. So a developer can focus on only one layer. And the point that Linda was saying about if there's an error, you can help debug it because you can isolate it to that individual layer, also good. Okay. The student's computer is part of the home local area network. We hear local area network, what are we thinking? Network in a small geographical area. Who owns all the infrastructure? Generally the people who actually run there. Our school is a local area network. Who has to run all the different material here? We have to run it. As opposed to a WAN. WAN standing for Wide Area Network, which is a network over a large geographical area. And does it own its own infrastructure? No, it uses third-party cabling, so it might go over OpenReach or Virgin, whatever. Okay? So what characteristic are we going to give for a LAN? So because they've already given small geographical area, we're going to say it uses its own internal hardware. And now we need to describe the benefits of the student changing the home LAN to include wireless connections. What is the device we use? So do you remember we've talked about this before, that in your house, you refer to that thing in the middle, Wi-Fi box or router, whatever, and we've said we need to break that into pieces because I refer to the device in my house. I do this as well. I call it a router, but technically it's more than a router because it receives fiber optic communications and turns it from light into ones and zeros. That means it's a modem. It also routes packets over the internet from one place to another. That makes it a router. It also provides wireless connections on my local area, which means it's a wireless access point. And it also works to connect my devices on my local area, meaning it's a switch. So technically my router is a modem, a router, a wireless access point, and a switch. And it does all 4 of those things at the same time. In this case, it's saying to include wireless connections. So what is the benefit? Well, if you don't have wireless connections, what would you have? Connected using Ethernet. So think about it from that perspective. They're all connected using Ethernet. What kind of problems do you have? Limited range, you'd have to be somewhere close to it when you'd be able to do it. Messy cables together, it's like a trip hazard, isn't it? Right? Is it going to be easy for your friend to come over and connect to your network? No, so it's going to be much easier to connect new devices, isn't it, over a wireless network? Let's see what else I've got here. So I've got loads of examples. So it allows more devices to connect, like mobile phones, things that doesn't have an Ethernet connection. Oh, what does every device need to connect to a network? Network interface card. And Nick, Easy to connect new devices. Oh, example, a guest could come over and connect. Bless you. Home is likely a small area. So the home being a small area, why is that an advantage for like Wi-Fi? Because what can a problem with Wi-Fi be? In like a building like this, I currently cannot get Wi-Fi on my iPad that I'm doing this on. God knows why. Because we've got multiple wireless access points. One's downstairs, maybe it's on the blink or whatever. And why can't I connect to it? There's walls in the way, selfish people in the way, right? Physical objects, and all of that's going to massively restrict it. You might have a router that says, or a wireless access point that goes over 100 meters, but that's over air. Every physical barrier can be a problem. And in those situations, you might be better off with Ethernet if it's over a longer distance. It says it's cheaper to purchase. Let me just write down a few points, shall I? So in this case, allowing more devices to connect without, I suppose I should specify in here, without an Ethernet cable. And then applications such as mobile phones, because this is an example of where that would be the case. There are more things I could have written down. I'm going to stop here for the moment. Some of the classic examples are there. There's actually the 4 marks in there. State 2 drawbacks of changing their homeland to include wireless connections. So now let's talk about some of the issues that could happen. So please, go on, Razan, give us an example. Absolutely. So because it's wireless, it's much easier to intercept what you're doing. Any other... I hope not. There we go. So that was the big drawback, isn't it, about Wi-Fi? Anybody live in a house where your router is at the bottom of the house and you live far away and it's terrible connection? Yeah. I've got it in my house. Like, I've got an extended house. Don't worry, it's not very big. Still tiny. But there's actually a big brick wall in between the two of it. What's the connection like in the room I live in? Terrible, because it's going through a big brick wall. It's really affecting performance. In the same way, you might be able to roughly pick out your neighbor's internet, but it's probably not a very good connection. If they're going through a brick wall, through another brick wall, it's going to affect it. People. So my 2 I've fallen down on. You can say a lot of different things here. I've said that it's less secure as easier to intercept. That's what Razan's suggestion. I think it's a really solid suggestion. And the other one being that the inherently slower rate of transmission in comparison to a wired network, because the network could be distance from the wireless access point, and whether you're going through a physical wall will affect the performance as well. Now, of course, if your Ethernet cable is long enough, it will create an issue as well, but it'll be less noticeable. Oh, lovely. Look at this. Fill in the gap. I love filling the gap. Come on. One form. Oh, so this is about characters and images. This one's about characters. Binary numbers can represent different forms of data. Yo, characters. Thank you for your answers. What are the 2 different character sets we care about? ASCII and Unicode. Remember, I gave you the update. Is there a difference between ASCII and extended ASCII on the syllabus now? Both of them will use 8-bit. So ASCII is 8 bits. So we're just clear about that. One form of data is characters. Complete the description of how computers represent characters in binary using the given list of terms. Not all terms will be used. A character set stores. You know what? I think you should have a go at trying to fill this out. I'm going to pause the video, and you guys are going to try and fill it out. Okay, guys. So looking through these questions, we've just had a really interesting conversation, I would say. Because the first thing it says, a character set stores. So does it say which character set? No, it just says a character set. Stores what of the characters? And what are we thinking for the answer for this one? Because some people said some. But ultimately, let's say you got the ASCII character set. I can't represent emojis using ASCII. Well, I suppose I could do it with 2 separate characters, yeah? But that means that it can represent all of the characters that are in ASCII. So from the perspective of the computer itself, although there may be other characters out there, it can only ever represent the things that are in its character set. So the first thing you'd have to say is, the first answer is all. Character is given a unique binary code. Lowercase and uppercase letters are given different. An example of a character set is ASCII. This character set uses 8, and they didn't put 7 in there. So I guess for that reason, because that would be a bit cruel, wouldn't it, really? If the code value for the character F is 70, what is it for L? So you remember how we do a question like this. F, E, F, G, H, I, J, K, L. Fine. Saying to help out, so then you can put a number and you can go. Do you remember a question like this as well comes up a lot of the time where it asks you then to convert between binary and or as part of the question. So the answer is 76. So the next bit is image representation. Being that we've done character representation and image representation we're about to do, what's the one we got missing? Sound representation. And it's possible sound representation is not in here. So let me just quickly talk about it. What are the two factors that affect the quality of an image? Resolution, which is the number of pixels, and color depth, which is the number of colors you can make. So the number of bits per. What's an image made out of? Individual pixels. Sound. What are the two factors that affect the quality of sound? Bit depth and sample rate. Sample rate, how often per second you sample the amplitude of the wave, and the bit depth is the number of ones and zeros you do to record the precision of that wave. Anyway, okay. The binary numbers represent images. The table shows the colors that are used in an image and the binary value for each color. How many colors do we have? We've got 4. Hey, being is that we've got 4. Actually, what's our color depth? How many bit color depth? 4-bit color depth, yes? Being is that we've got a 4-bit color depth, how many colors could we have in total? 16, because it would be 2 to the power of 4. Yes? Just so we know. The metadata states that the image is 3 pixels wide by 4 pixels high. This is not what you call a large pixel, a large image. The data in the file starts in the top left of the image and goes from left, right to top to the bottom. What is meant by metadata? Okay, is this metadata?
Yeah.
No. The raw data that makes up the image is the only thing that is not metadata. What else could be metadata? The width and the height of the image. The color depth, metadata. The date it was made, the author of it, the file size. All of this is metadata. What is the only thing that isn't metadata? The raw data that makes it up. The ones and zeros that actually make up the thing, which is actually most of the file, clearly. So I would say metadata is data about the data. I heard an audible groan from the class when I did this description. I will hear you. But this is a description we need to know. Metadata is data about data. Now, I've talked to you about what metadata actually is. But it's data about the data. Data about the raw data is not included. Okay, on to the next question. Okay, guys, we have a raw stream of data here. And we have been given information, have we not, about what these different ones and zeros count for. A grid is given for the image. Each square is 1 pixel. Write the name of the color. So what we'd have to do is split this into groups of what? 4. So I'm going to split it into 4s, and then we're going to turn each of those into a... Man, there's so many. 000 is red. Oh, I did it in red. Red. What's next? Purple. I don't question you. Well, I do all the time. What's next? Blue. And then, what's next? 0010 is green. This is a disgusting picture. I don't know what it is of nothing. No offense to whoever wrote this. And then blue. And then finally, guys, what's next? Oh, I've just noticed this. Oh, we know we've got a bottom row as well. Oh, God. Purple, purple, purple. Is it? Purple. I want to be lazy by doing purple, purple, purple. But if I am and put down P, then you're going to write down P, aren't you, for the real thing? So I'll make the effort. Finally, red, green, blue. Oh, I'll do it. There you go. Red. I'll do this. Does it make you happy? I'm not doing that. Shh. Oh, we did this. Excellent. A color depth of 4 is used. This means 4 bits are used to store the color for each pixel. State the maximum number of different colors that can be represented in 4 bits. We did this. 16. Hey. Okay, and the next question is all about turning the number of bits into the number of different colors you're going to make. This is something that people really do struggle with. So let me just take a moment to describe how that's going to work. If you have a color depth expressed as a certain number of bits, so that could be, I don't know, 1 bit or 2 bit or 3 bit color depth. The question is, how many colors can that make? So if you have 1 bit color depth, that means you have a single bit. So a single 1 or 0. In this case, 1 could represent red, 2 could represent, I don't know, blue. In this case, you have 2. 2 colors can be demonstrated, can be represented. And if you have 2-bit color depth, you can have 4 colors. And if you have 3-bit, you can have 8 colors. Essentially, as you're going down this way, it's doubling. Or another way to think about it is that it's 2 to the power of the number of bits. Wait, what do I mean by that? So 2, 2, 2, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. If I had, for instance, a 6-bit color depth, that would be 2 to the power 6. 2 times 2 times 2, 6 times. And that would mean that you have 64 colors. In this question, it's simply asking you if you had a color depth of 4, aka 4 bits. If we're using 4 bits for each color, well, if 3 bits was 8 colors, then 4 bits would be 2 to the power 4, which would be, that's right, 16 colors. It then says the color depth is increased to 2 bytes. Did you remember what we mean by a byte? That's right. Each byte is 8 bits. So if we have a 2 bytes for the color depth, it means we have 16 bits, which means that every single pixel could create 2 to the power 16 colors, which is about 65,536 colors. Big increase. So that's going to mean that we can show a lot more qualities, a lot more colors. So the number of colors can be increased dramatically, which would obviously increase the quality of the image. Well, why don't we always just have as big a color depth as possible? Because that would mean that we can show more colors and it can look far better. Well, what's the one big downside of it? That's right, the downside is it's going to massively increase the file size. In fact, a follow-on question could be something like, how much larger would the file be now? Without even knowing the resolution, aka the number of pixels, we can say how many times larger this file will be, because previously each pixel required 4 bits, and now each pixel requires 2 bytes or 16 bits. So if we've gone from 4 bits per pixel to 16 bits per pixel, the file size will increase by 4. Okay, great. We now have a question on compression. A student has a text document and an image file that need to be compressed separately. The student needs to reduce the file size of both of these files as much as possible. Now remember, there's 2 different types of strategies for compression. The first of these would be lossless compression, and the second of these would be lossy. Now both of them start with an original bit of data, represented here by my image of my person. They both get shrunk down to a smaller version, and then with lossless, at the end of it you have a perfect match for the original. So both of them compress it, but with lossless, no data is permanently lost, and when you decompress it, it's a perfect match for the original. With lossy, you have the original image. It compresses it even further because with lossy, data can be permanently removed. Well, that's because we're not that sensitive to some things like the number of original colors. You might not notice one slightly different color to another. With sound, there'll be sort of sounds that you can't hear that can be removed permanently. and then but though when we recreate it, you might visually look the same or it might look similar, but data has been permanently removed. That's great for things like images, in fact, actually, because they can be very large. But with lossless, let's say we're trying to do something else. We're trying to reduce some text or a string. So we could have face was my original string. That gets compressed to some smaller version of it, some smaller number of it. And then when it gets decompressed, what will it look like now? If we're using lossless compression, if we started with the string face, what would you end up with in the end? That's right, you'd have a perfect version of the original. No data is permanently lost. In lossy, let's say you started off with face, and now when you shrink it, data is permanently removed. So it's shrunk down to a smaller file. But when you have it at the end, what's going to happen? That's right, some of the text might have actually changed. Maybe it starts with F, and then it will be 4, and then it will be like exclamation mark, and then maybe E. Who knows? The point is, because data is permanently removed, it's very poor for things like text. Okay, let's go back in here. So a student has a text document, and then we're looking for the most suitable type for compression. Now, what are we going to use for compression for text? You know, if we use lossy, data will be permanently lost. That doesn't seem so smart. So the answer would be lossless. And now we have to justify it. Well, the big deal is that no data is lost. No data is lost permanently. And we could extend that by saying that it's reconstructed back to the original. aka when you decompress it, it's a perfect match for the original. Okay, great. Well, this is still knowledge. Now we need to apply it to this situation. Why is it so important? Well, the issue is that text files will not work if any data is lost. Imagine in ASCII, if you lose an individual 1 and 0, then some of the text could actually disappear. And I'm saying that any lost data could change an individual character. You could extend on this again or expand on this again by making reference to things such as you could say, for example, an A could become an exclamation mark, etc. The next one we have to look at is the image file. Now remember, the goal is to compress it as much as possible. And you can have lossless compression with image files. However, the big downside of lossless compression with image files is that they will remain pretty large. You could be talking about something as much as the difference between, say, 20 megabytes and 200K. And ironically, you may not even be able to spot the difference because sometimes it's not that perceivable. Of course, if you compress it too far, it starts to block in, you will see the difference. So I'm going to suggest, well, the answer is lossy because it will compress it the most. And our justification is it's going to reduce the file size most significantly. Okay, well, why didn't we just use lossy last time with text? Well, remember, with text, we're going to notice if a character changes. So our justification this time is we'll say that the end user may not notice the difference. Because bear in mind, the changes, as I mentioned earlier, will be things like an individual color change, that sort of thing. Great, we're now on to a network security question. We have to tick one or more boxes. Please pay attention to this bit here. Sometimes it says one, sometimes it says one or more, and it's really important we pay attention to which one it is so we can answer it correctly. Essentially, we're given threats on one side and methods of prevention on this side. And then at the end of it, let's do a question at a time. So first of all, spyware. So spyware, this is software that runs on your computer in the background, looking at sort of maybe what websites you're going on. It's inspecting the things that you're doing. What can we do? Well, one of the obvious ones you can do is anti-malware. It will check for that software, and if it sees it, it will place it in quarantine and make you aware that it's found it. What else could we do? Well, if you remember penetration testing is when people test software, test systems to see if there are any weaknesses, and if it finds any weaknesses, you report it back with penetration testing. Encryption, that's when you take data and you turn it into sort of ciphertext that will be unreadable by you unless you have the cipher key, so keeps the data secure. I don't see how that works with spyware or penetration testing particularly. Firewall is about inspecting ingoing and outgoing traffic and searches for packets, looks for packets coming from suspicious places, and if so, it drops the packet. Potentially could be the case with spyware. It depends on the nature of it. If it's being sent to malicious websites, if it's reporting the data to malicious websites, you could say it could be a firewall could be used in that case. Although I think in general it's probably, well, it depends. It's not going to be true of all circumstances. Well, anti-malware definitely will be. A brute force attack. So this is where people are going to try loads and loads of different combinations to try to get into your system. Typically checking lots of different passwords and things like that. One of the obvious things you could potentially put in is penetration testing in this case, because you could get somebody to check all the different combinations and see what happens. Probably should do something like us after a certain number of attempts it fails and reports back. Anti-malware, well, this is not software, this is people physically testing it, don't really apply. Encryption, I guess encryption could work in the sense that after somebody gained access, they can get security. Although, of course, a lot of times your password is associated with your encryption key, and it will be your cipher key, so probably not going to work in this case. But firewall could be searching for people trying to gain access. So if someone's trying to access, try and take in your username and password from an external website, it could detect that it's trying to move this kind of data and then drop those packets to prevent that kind of access. If we think about it as well, things like a denial of service attack, a DDoS attack, firewall is the perfect place for it. It's detecting repeated suspicious activity from certain IP addresses out there on the internet, and if it detects them, it will just drop those connections. Okay, data interception, or a man-in-the-middle attack. So this is where you're spending data from one place to another. Somebody intercepts it as it's been traveling from one place to another. Anti-malware, well, of course, this is just software that you got yourself, so it'll probably not be the case. Penetration testing, well, this is not about testing if a system works or not, so probably not appropriate. Encryption, now encryption will not stop data interception, but of course, if you intercept the data and it is encrypted, then that is useless to you unless you have the cipher key. So I would say encryption is a really good way of preventing, well, it doesn't prevent data interception, but prevents the problems associated with data interception. And firewall, well, at this point, this is data that's left your network, so firewall's probably not going to help because it's already left. SQL injection, so this is where people put code into a website to run SQL queries, like it can really run haywire. So online, think like online systems like Amazon, you type in on a form, you put in information, searches, looking for the thing you're trying to buy. Well, it's possible to put in certain reserved characters and force an SQL a query to run. You think about it is that there's not just a web server for Amazon, there's also the SQL database keeping track of all your different things. And so if you could run an SQL injection, you can make it maybe drop or delete all the data, which is definitely not a good idea. Of course, big websites like Amazon, they've blocked these kind of things, but smaller websites potentially can be affected by SQL injection attacks. Anti-malware, well, this is not software, this is an individual attempting it, it's not going to work. Penetration testing, this is when you test to see if you can run SQL code in this context, and then it will report back and somebody will say, look, you've got weaknesses here, you need to patch. So penetration testing absolutely would be a good idea. Encryption, that's an interesting one, but of course, once you've actually run, SQL data can't be encrypted in the sense that once you've run in the SQL, if you can actually run it on the system, then it will be able to run access. Unfortunately, at that point, it can't do. Firewall could be a good shout, though, because it could detect incoming data, and in that case, it could block it from certain suspicious websites. Although realistically, this might be somebody just running one thing, so it'll be difficult for firewall. So really, penetration testing is your big one. Then it's asking us to identify another type of threat. I mean, there's so many different ones you could mention here. I mean, we talked about one, didn't we? We talked about DOS or more likely DDoS. So that's denial of service, of distributed denial of service. So this is when multiple requests are made of a server, and then the server is flooded with these requests, and the server eventually can just like fall over. And that happens at websites. You might notice, like at Christmas, certain websites sort of restrict access because effectively we're doing distributed denial of service onto a website, and it's just trying to stop load so it doesn't collapse. What else you got? Your phishing emails, so you could make a request for someone to click on your link on a fake email, and then they could get entrapped that way. You could have shoulder surfing. Shoulder surfing is when somebody's looking over your shoulder, looking for a PIN code or your password. So you'd have to make sure that the person, checks to see what's happening, to see that no one's looking over their shoulder. All good examples. Okay, now we're on to memory and secondary storage. An artist has a computer that they use to create images. Their computer has both hardware and software. Makes sense. Hardware includes primary and secondary storage. Explain why a computer both needs primary and secondary storage. Well, if you remember, primary memory includes things like RAM and ROM and cache. Why is this stuff important? Well, this is the only place where data and instructions that the processor can access. So, and if you remember, ROM would store sort of boot up instructions, BIOS, that sort of thing. RAM is going to store currently running programs and data. And cache, well, cache is going to be your frequently used instructions ready to be fetched efficiently and quickly. What about secondary storage then? Why do we need that? Well, of course, here's the problem with RAM and cache is that they're volatile. Do you remember what that means? So yeah, that's right. Volatile means that when the power goes off, all the data disappears. So your first thing when you turn your computer on, your CPU may look to fetch instructions from cache. Can it do? No, there's nothing in cache because it's volatile. Well, then it tries to fetch it from RAM. Can it do it? No, nothing in RAM because the power's just been turned off. So it looks in ROM for non-volatile storage. However, ROM can't change, so you can't permanently add data in there. So what we need is a permanent non-volatile storage where we can read and write from. And ultimately, that's what secondary storage is. So we're saying that secondary storage stores data permanently or long-term. So without this, the data could not be saved when the computer turns off, i.e. you'd lose it forever. So you're looking in your Word document, if you didn't have secondary storage of some kind, or indeed cloud storage, which ultimately is secondary storage but at a different location over the internet, you wouldn't be able to save it because it's held in RAM. As soon as you turn it off, it would disappear. Give one example of a secondary storage device that the artist's company will have an example of the data that will be stored on it. So this artist, remember, has a computer that he used to create images. So we're trying to think of some kind of secondary storage that we'd use. Now, do you remember the different types? We had magnetic storage, so typically a magnetic hard drive, which can store lots of data, very large capacity, fairly cheap per megabyte anyway, but it's got moving parts, so not very portable. It could easily break in the sense that if you shook it around. And then you've got solid state storage, which has got no moving parts, so great. It's very small, durable, portable, so stick it in things like your smartphone. Invariably these days, things like tablets and laptops, etc., all have flash storage of some kind. Very quick, but can be more expensive per gigabyte, although that's changing all the time. And then finally, you've got optical storage, so like this is CDs and Blu-rays and stuff like that. Well, I think most likely they'll be using a hard drive, a magnetic hard drive, or solid state drive of some kind. So I'm going to go put that in. What sort of things are going to be in a solid state drive? Well, I guess things like the image editing software and the images themselves. Okay, great stuff. Next, we're on to virtual memory. So as we said, primary memory, RAM, ROM, and cache is where the CPU fetches instructions from directly. However, eventually what can happen is that RAM has too many currently running applications and starts to fill. And I guess the decision could be at that point, it could tell you to shut down some of your applications. But truthfully, you may have lots running, but you're not only actively using some of them. And so what can happen with virtual memory, if we remember, is where a section of secondary storage sort of pretends to be RAM. And what you do is you move processes that are not currently active, aka you're not using, and move them into virtual memory. And then that frees up space in RAM for you to put active, currently running applications. And then what can happen is that as you want to switch back to your older application, it moves from virtual memory back into RAM, stuff from RAM into virtual memory, and you have this sort of dance backwards and forwards between the two. We've got 4 statements about virtual memory, and not all the statements are correct. We've got to tick true for the statements that are correct and rewrite any statement that's incorrect. So a section of primary storage is partitioned to act as virtual memory. Now, if you're just listening to me, which part of storage, what type of storage is used to act as virtual memory? That's right, it's secondary storage is used to act as virtual memory. Great, on to the next question. Data from ROM is transferred into virtual memory. Data from ROM is transferred into virtual memory. Now, do you remember what I said to you? I said RAM is where currently running processes and data is held, running applications and data is held, and only the non-active of those go back into virtual memory, and there's a movement of data between virtual memory and RAM so that the currently running applications are in RAM and the inactive currently running applications are in virtual memory. ROM was used for your basic input-output system for your boot-up instructions. This is not what's going to happen. So it's RAM that we should be talking about. Virtual memory is needed when RAM is full or nearly full. What do we think of this? Yeah, that's right. That's exactly why it's used, because when RAM is full, that's when you're going to move currently running but inactive processes into virtual memory to free up space to allow you to run new applications or create space for it. Data from virtual memory is transferred back to secondary storage when needed. Now, this seems like it's correct, right? Because data from virtual memory is transferred back when needed, but does it transfer back to secondary storage? No, it's back to primary storage. Well, in this case, RAM. It's transferred back to RAM. And finally, we have a question on utility software. So you can imagine that there are software that's written to support the running of the computer. So that would be the operating system, with things like a user interface and memory management and peripheral management, processor scheduling, these sort of things that the operating system does. But you also have other software that's used to support it. Examples, things like a virus checker, anti-malware. That's a utility software. So we're talking about examples of software that's used to support the running of the computer. So I'm saying to monitor and maintain a computer system. So we're thinking about, like I say, things like anti-malware. What does it do? In the background, it's checking to see, are there any suspicious applications or data? And if it does so, it puts it in quarantine. And that's classic kind of utility software. You're not actively using it, sort of working in the background to support your computer to work more efficiently. Okay, and now we're on to a question about networks. Bear in mind, there can be lots of different questions in this topic. It could be local area networks versus wide area networks. It could be about protocols. It could be about topologies, mesh topology versus star topologies. In this case, it's asking about client-server networks as opposed to something like a peer-to-peer network, although a peer-to-peer network is not mentioned here. It's literally talking about a client-server network. If you remember client-server networks, they're pretty much like the networks you're going to have in your school. Your individual computer, you get to log on to it. It's a client. You can imagine that you've got, individual clients, machines where you can access information, and then there'll be a server. So you've got a server that's going to serve up information to clients. And it's an imbalance relationship in a client-server network where essentially this server in the school will be like a file server Client logs in, file server serves up files to all these clients. Could also be a printer server, could be a proxy server, web server, serving up internet connections to all these different clients. But the whole point about client server is that you have an imbalance where a server is just serving up more powerful machine, serving up content and data to clients. In this case, the scenario is the artist uploads images to be displayed on a website. This is a client-server relationship. Remember, essentially, websites are just remote computers, aka computers that aren't necessarily next to you, where they'll be hosting all the images and HTML text, etc. for that website. When you go to a website, you type in a URL, www.google.com or whatever. Remember that website, the URL was taken, a DNS system, domain name system, takes that URL, looks to see if it can actually find the matching IP address to it through several of top-level domains, etc., through resolvers. Eventually it's resolved, the IP address is returned to you, your web, you then have it routed so that you can actually find that IP address out in the world. When you get there, there's a web server, it then actually serves up this content, generates this web page, and then you can view it. A lot of technology going on in the background for that to happen. You can also, I don't know if it's going to come up, there's the protocols involved. So the protocols to allow you to have transmission over the internet, the Transmission Control Protocol, TCP, and also, of course, the concept of HTTP, Hypertext Transfer Protocol, for sending individual web pages. Although if it's the images being sent up, and you're trying to upload your images to the web server, probably over file transfer protocol. Anyway, that's all talking around the topic. Let's get back to the idea of a client-server network. Identify the computer that is acting as a client in this scenario and justify your choice. Well, as discussed before, remember the school that you work at is that your computers that you work at are clients, and then the server will be a web server, a file server that's holding data for you, probably locally in your building over a local area network. And so your computer is much like this one here where you're doing this work. It will almost certainly be a client. The artist's computer itself will be the client in this situation. And then in this scenario, the artist is uploading images to be displayed on the website. So how can we justify that it's a client? Well, in this case, it's not serving it, it's making requests to the web server to upload its files. So it's sending requests to the web server to store or upload its files. If you remember, when you're on the client, you make requests to the server, the client makes requests to the server, and the server serves data back to the client. That's the relationship that exists in here. Client makes requests, server serves up the data or the request, or fulfills the request. What are you making requests to do? Well, in this case, it's to upload the images. You could say something along the lines of the files aren't saved locally on the client, the files are saved onto the server, like on your computer. The files aren't on your computer, whether you're sitting in front of in a school. The files are saved on the server. So you can make that point as well. Okay, and let's look on the other side of it. So we need to also identify the computer that is acting as the server in this scenario and justify your choice. Well, in this case, I guess the clue kind of is in the name. You're uploading to a website. What is the name of the device that is holding all that data? As we referred to earlier, it is a web server. While a client requests or makes requests, a server receives the request and then responds to the request. So it serves the client. In this case, what are the requests? Well, it's going to be storing the images. Okay, like I say, this is a very big topic, many different areas and networks, quite specific areas, classics that come up, or comparing a switch to a router. If we're comparing a switch to a router, we talk about a switch working over a local area network using MAC addresses to connect devices together, while a router routes packets over the internet using IP addresses. What other classics? Yeah, looking at different protocols about which ones are suitable for sending emails. SMTP, Simple Mail Transfer Protocol, for sending emails to a web server or between web servers. IMAP or POP, used to receive emails from an email server, FTP for sending files, HTTP for looking at web pages, or HTTPS for looking at secure web page. Lots of different types of questions could be answered in this one here. Okay, now we're comparing and contrasting open source versus proprietary licensing. So these are two different basically philosophies about software development and about how you make it accessible to people. The artist is working with programmers on the development of a new piece of software. So what do we mean by open source? Well, with open source, you make your source, what's open is your source code. So people can see the source code, the code that you have written to be able to actually make that piece of software. Why would you do that? Well, essentially, it's something where you are making it available and open for people to volunteer their time to work on writing this code, and so that other people can make use of your software. And being as that it's open source, it means that you're not going to charge for your code. So it's going to be free to use for people to gain access to. Examples of this in the real world, well, Android, the operating system for Android, is an open source piece of software. Google do not charge you to use Android. Why would it decide to do that? Well, in its case, there's something called Google. There's Google services such as searching on Google, Google Mail, YouTube, like all of these sort of packaged in with use of Android, and as a result, it makes sense for it to do so. There are editing software that exists out there that's open source. But the vast majority of software, realistically, that you're going to be using is proprietary software. What does this mean? Well, it's closed source. You can't look at it. However, it means that those people there will almost certainly charge you to use the product. You can be a bit more guaranteed of the quality of the software in general. There's going to be more support available for it. And probably additional training and stuff. So the kind of photo, if we go back to the idea of photo editing, things like Photoshop, although you shouldn't use about name brands, you don't talk generic, those will be proprietary software, or the Office 365 stuff like Word and Excel, or proprietary software as well. Okay, so let's go through it. The software will allow users to edit images on devices such as mobile telephones. They are considering releasing their software as open source instead of proprietary. Describe two benefits to the artist and program of releasing the software as proprietary. Now, I said that that with open source, it's free to use. Now, that's great for you as a consumer, the end user, but of course, it's not great for the people on the other side. They're providing their labor, they're writing their code, and they can't sell the money. But if it's proprietary, it means that the author can actually earn some money. How do they earn money? Well, they can either sell a license to use the software, or actually selling individual copies, but typically, by selling a license. Okay, great. But what other advantages are there? Well, since no one can see their code, you can't, for instance, insert malware by looking at the code and figuring out how you could hack it. And also, you can keep your intellectual property, right? People can't just copy it and change it or take excerpts from it. Although in theory, there's supposed to be some kind of agreement that people can't just, you agree the terms to using open source even, because you can say that, some people say you can use it however you like. Some people can say you can reuse it, but you ask for permission. Some people say that, it can't be reused, but it is free to use. So, but of course, once you've made the software available and people see your source code, you can see how it could be quite easily taken. So this is proprietary. No one can see their code. So this means that in many ways, the advantages could be that you can't edit the code and it can't be copied or shared. What was the advantage of this? That no one can edit it. But what was the problem? That, for instance, you could look to see where you could add things like malware. Great. Well, then let's think about the other side of it. Are there any benefits to the use of releasing the software as software? Well, you're not making any money out of this. So what's the advantage for you to do it? Well, this is for users. So this is not from the point of view of the person writing the software. So if it's freely accessible, freely easy, if it's open to use, you don't have to pay for it. And you could even potentially, change it or distribute it, but with permission. Also, some of these open source projects turn into an opportunity for other people to help out and help edit and improve and tailor the software. So that can be a really powerful thing for the community and for users. It also might be that you see that some bugs in there, and of course you find bugs in software, but this time, because it's open source, potentially you could even go and do something about it. Okay, so now we're on the 8 marker on implications of computing. Remember, the way that these questions will work is it will want you to think about some kind of scenario. Maybe it's about implications of AI in maybe creating students' work. Could be a question on social media and its implications. Could be about digital divide with the use or access to banking services. It could be almost a wide range of different things. And what it will want you to do is consider the effect on typically you as an individual, and maybe from the company's viewpoint or the system's viewpoint, like whoever's running the system. What's the advantages? What's the disadvantages? And remember, knowledge, what you know about it, and then apply that to the scenario. So in this context, in this question, it's talking about a shopping center that has a security system that includes CCTV cameras to record activities in the center. And you can imagine immediately there's concerns about holding information about people. People don't want to be recorded anonymously and storing that information. You can see how people were not keen on it. Flipping on the other side, you could prevent certain crime that's happening. Flip from the side of the shopping center itself. Does it have legal requirements? If it's holding information about people, the Data Protection Act says that you only should hold it for relevant reasons, for make sure it's kept secure, that you can only use it for the purposes that are stated. Lots of kind of concerns about going about on here. The security system is being upgraded to include the use of facial recognition to identify and track the movements of and record individuals through the shopping center. So on one level, super powerful. Let's say any crime was committed. Now you know exactly who did it. Let's say you wanted to find about who customers came in. You could find out what kind of customers came in on certain times, what kind of things they bought. You could have targeted campaigning. So useful from that point of view. Of course, from the other point of view as the user, do you like the idea that someone's keeping this sort of biometric data about you? What are they going to use it for? Is it fair that these people are tracking you? Is that proportionate? How else could they use this biometric data? Facial recognition is used to do all sorts of things. It opens up a huge amount of concern. And so we have to discuss both the positive, the for and against, the impacts of this upgrade, considering the ethical issues, the privacy issues, and the legal issues. So we need to go through each of these, saying what we know, and then applying it to this context, and really, this is just about making good arguments. You can pick up a lot of marks here. Don't be thrown. Whatever comes up, you're very knowledgeable. There's a lot of good things you can say here. It's not, yes, let's say you can't remember the specific law, but you can talk in general terms. You can make a good, strong argument. So don't panic, do your best on these questions. Like I say, there's many things that we could say, but why don't we start from the point of view of legal issues, because that's something that we have covered and we can talk about in terms of knowledge. Legal, we can talk about the Data Protection Act. We can also talk about the Computer Misuse Act. And finally, the other bit of legislation we need to know about is the Copyright, Designs and Patents Act. Now, I'm not saying we need to talk about all of these, but let's consider the implication on something like this. Well, I think the big one here is the Data Protection Act. I'm not going to write out an answer, but let's talk about some of the things we can talk about that we could consider. So the idea is the Data Protection Act is that if you are holding data about somebody, and someone's face would definitely come under that remit. You're supposed to hold information only for relevant reasons, that you have to keep it secure, that you shouldn't transfer it to the other people, that you can't sell on data without you're given stated permission about how you're going to use it. So we could say things like the Data Protection Act needs to be followed, i.e. has to follow these rules, especially keeping it secure, otherwise they could be fined. And we can apply that by saying the customer is informed the system is used for. So what is the data being held for? And if it's not held, or it's held for longer than is reasonable, then it could be a problem. If the data is not held securely enough, especially since it's quite personal information like facial recognition stuff, you could be fined. The center is private property, so customers can choose not to enter, is the argument you could say. So you could say, in a public place, you're not supposed to hold this information, but they've made, because the place is private property, it's like if someone comes into your home, you can have the right, they have the right not to enter. So therefore, there's different rights that can be associated. And it can be used to identify people committing crimes. So if there's some committed theft, you can actually use that to find that person and to help secure it. But what about ethical issues? So this is not the law. This is personal to each individual about what your ethics are, and you sort of argue it. And don't just say what you think is the case. Try and think about it from the point of view. You might think that it's terrible that this is the case, but you need to see it from both perspectives. So you might feel different. So some of the things we could say, users could feel safer because they know that that any crime is being tracked, that there's no anonymity here. Users could not have not done anything. So the principle in law normally, or the principle in life, is that if you're innocent until proven guilty, but this way people are being recorded irrelevant of whether they've actually done something or not. People might feel unsafe because they're being watched or feel not very secure. They may be unaware that they're being recorded, so you'd have to inform them that this is the case and have to give consent to this sort of thing happening. Users don't know the videos about them and the movements are stored and how it's being used. So this is also, referring to the Data Protection Act. And then finally, if we talk about privacy, I mean, this is all pretty obvious stuff, but right, you're going to feel this is a big invasion of your privacy, and because you're in a public place, you can be legally recorded by anyone anyway. However, people are not going to like this sort of situation. They may feel like they're being watched. Users haven't given permission to being tracked. Users may not know the system exists. So, a lot of the same points here. And you can see how, even though you might feel stumped, I bet you all the things I've said right now are things that you were considering. So don't panic with a question like this. Make sensible, cogent arguments, and I'm sure you'll get a lot of marks. Finally, we're on to embedded systems. Embedded systems, you remember, are systems where typically they're built for a limited functionality built into a larger device. We're talking about things like automatic lights on a car, or a heating system inside a house, or the temperature regulation, or timings inside a microwave. And data is normally, as in the instructions for it, are normally held on ROM, because the idea is that it's not like a conventional computing system where it's on secondary storage and then loaded from secondary storage into RAM ready to be used. These things are ready to go immediately from ROM, but generally can't be updated very much. So a car comes with many embedded systems. For example, parking sensors. Identify one other embedded system that can be found in a car. Display what's embedded there. Well, I think I said one. So automatic lights could be one. Really, by explanation, it's saying what's the reason? Well, we said limited functionality. So I'm saying it's limited functionality. I mean, ultimately, the system is just going to turn lights on or off depending on current lighting. If I remember, I also said that embedded systems, the instructions to run it will come off ROM. And ROM is read-only memory, so it's going to be hard to change the functions for an embedded system. Okay, great stuff.